let us compute the limit as x goes to infinity of arctangent of x. So there's a couple points here that might cause a little bit of problems. First of all, hold on, x goes to infinity. We haven't seen that before. And then also arctangent of x. What exactly is that? So let's look at arctangent of x first. And before I do arctan, I'll remind you of what the graph just of tangent was. So here's the graph of tangent. It goes up and it keeps on having this sort of periodic behavior where at plus pi over 2 or minus pi over 2 that what you get are these asymptotes, these vertical asymptotes. And they're important enough that maybe I'll even sort of label it that this is going to be pi divided by 2 over there, and at this one, looks around there, going to be minus pi divided by 2. So tangent is a periodic function, and this is its graph. But I'm not asking about tangent, I asked about arctangent. So the way these arc trigonometric terms work is that they're an inverse. In the same way that e to the x and ln of x, the natural log of x, that those are inverse functions, or the same way that x and 1 over x are inverse functions, tangent and arctangent are inverse functions. So if you have the graph of a function, you want to graph its inverse function, you alternate the role of y and x. So this is what the graph of arctangent looks like. We've got this graph of tangent. We have the line y equals x that flows through here, and I want you to imagine that I flip this picture around the line y equals x. And so then what I get is this graph here. That is my graph of arctangent of x. Sometimes I write it out in words, arctan of x. Sometimes you write tan with an exponent of minus 1 of x. Don't be confused. This does not mean tangent of x all to the power of minus 1, which would be read 1 over tangent of x. It's not that. It's not an exponent of minus 1. The minus 1 means an inverse function. I think it's a bit confusing, so that's why I usually just write out arctangent of x. But either way, you should see this symmetry here. We've got this line y equal to x that comes through here, and arctangent flips over the tangent. The other defining property that we have here is that for an inverse function, if you compose them in either way, so tan of arctan or arctan of tan, either way you compose them, what you get out of it is just the identity function. Now, I should say one quick caveat, that this only works for what we call this one branch of tangent. In truth, tangent is this periodic function. Here's a little bit of another branch, here's a little bit of another branch, but there's sort of this one major branch between minus pi over 2 and pi over 2. And arctangent is defined to be the inverse just for that branch. So this formula only works in the particular domain minus pi over 2 up to pi over 2. For the purposes just of computing what the limit was, all I need is this graph. So that's all I've left behind here. This is some graph, and as x goes large, that's what it means going to infinity, bigger and bigger, million, billion, trillion, carries on. It's going off and off far to the right. But it sort of flattens out on me. Yes, it's going off to the right, but it doesn't carry on up to infinity. It doesn't sort of oscillate or do anything weird. What it looks like is it just flattens out and becomes close to this one value. And in fact, we can talk about what that one value was. As you might recall, if I go back and I look at tangent, that at the value of pi over 2 here, the tangent was going to have a spike towards infinity at this value of pi over 2. So then for the inverse function, when we're sending it off to infinity, it's getting close to a height of pi over 2. So I'm going to claim that the limit as x goes to infinity of arctangent of x is equal to pi divided out by 2. That is what we are now going to call a horizontal asymptote, or I will usually abbreviate it as horizontal asymptote and HA. And I can ask the exact same problem here for the limit as x goes to now minus infinity. So that's me coming along, coming along, coming along. We have another one of these horizontal asymptotes, and if I go back and look at what the graph was, as it went down to minus infinity, we knew that that occurred at pi over 2. That is the 0 of the denominator in sine x over cosine of x. So this value here is minus pi over 2. That's where it goes to minus infinity. So in the inverse function, in arctangent, as it goes to minus infinity, it flattens out to a horizontal asymptote at the value of minus pi divided by 2. I really like this particular function, arctangent. We're going to use it a whole bunch in our course. Let's do the same trick, but now another familiar function, e to the x. So here's the graph of e to the x. And we've got the two different questions. What happens if it goes to positive infinity? What happens if it goes to minus infinity? I'm going to do minus infinity first, actually, because it sure looks like it's just flattening right out, getting smaller and smaller and smaller and smaller, closer and closer and closer to 0. And so I'm going to say that this indeed is just equal to the value of 0. I'm going to say that the limit as x goes to minus infinity has a horizontal asymptote at the height of y equal to 0. But what about what happens as x goes to positive infinity? I'm going over here. But exponential, it increases forever. It gets bigger and bigger and bigger and bigger. So this is not like this example where it got arbitrarily close to 0. If I wanted to be within 0.1 or 0.01 or 0.001, I could just go far enough to the left. But that's not true on the right. It never gets close to one value. It just always gets bigger. It hits 1 million, then it hits 1 billion, then it hits 1 trillion after some time. It just keeps on going forever. So we're going to say the limit as x goes to infinity of e to the x is just going to be equal to infinity. It is unbounded. And so for functions like this, you have this sort of interesting behavior. There is one horizontal asymptote and one where as the x goes to infinity, it diverges to infinity.